Continuing on with the development of the mathematics of what we do, we're going to think about a unit cell, so a small block of porous medium, one small distance on each side, and we're going to think about that mass balance as the amount of flow that's going in minus the amount of flow that's going out being equal to this change in storage with time. Now typically, because of compressibility, we really think about mass balance and not volume balance. So the first thing that we're going to do is convert these volumetric flows into a mass flux, and we're going to do that by multiplying by the density. So now we have a true mass balance equation. We're going to think a bit more about this mass that we're conserving. It's really only the mass of the water, and within a porous medium that only exists in the pores, and we'll assume for now that they're fully saturated with water. So that really says that the mass of water is the volume multiplied by the porosity multiplied by the density. So that's the first change we're going to make, and then it's convenient to work on a per unit volume basis. So we're then going to divide by the volume, the total volume of that cell, and we get that this mass of water per unit volume is the porosity multiplied by the density. Finally, we're interested in how this mass stored changes with time. So we're going to take the derivative of that product of porosity and density with time, and we end up with these two terms. One that describes the change in porosity with time, and the other that describes the change in density with time. Moving right along, we're really interested in monitoring the energy status of the water. So we need some kind of constitutive relationship that describes how porosity changes as a function of, say, water pressure, something you may be familiar with from your soil buddies, and also how the density of the water itself changes as a function of its pressure. So we're going to introduce these two terms, a compressibility of the water and a compressibility of the medium, so that we can relate the storage change to the change in energy status. Once we've done that, we can substitute this in, and on the left-hand side we have the divergence of the flux multiplied by the density so that we have a mass balance, and on the right-hand side we have a change in storage, but it's also related to the energy status. So it's getting us towards that place where we have one unified equation that can describe both sides of the mass balance. Just a couple more steps, we're almost done. The next thing that we're going to do is substitute Darcy's equation in for the flux on the left-hand side, and we're then going to simplify that using a notation that allows us to show all directions is just a subscript. And then we're going to expand this a bit and replace the pressure head with hydraulic head on the right-hand side so that we end up with the flow equation. And I'd really like you to be able to read through this equation, so essentially turn the math into English, and I would like you to memorize this form, this textual form of the flow equation. The divergence of the flux is equal to the change in storage with time. So now we're finally ready to go back and define the boundary conditions. After looking at the equations and developing them, we can see that we really have to define the boundary in terms of hydraulic head, capital H. We have two choices. We can define the value of the hydraulic head, or we can define the gradient in the hydraulic head perpendicular to the boundary. Every point on the boundary has to be defined for every time. And we're basically going to use one of these two types of boundary conditions, although the value of each can change in time, and in fact the location can change between a constant head or a fixed head or defined head and a defined flux. You'll also hear a defined head boundary called a type 1 Dirichlet boundary. That means that the primary variable being solved for, in our case hydraulic head, is being defined, or a type 2, a Neumann boundary, and that is describing the gradient in that primary variable perpendicular to the boundary. In reality, defining boundary conditions that really account for the influence of the rest of the universe can be a little bit tricky. We often have to rely on intuition, and we are usually using a boundary that is not quite perfect. That's the reason that we'll often have to go back and move the physical boundary of the domain until we find a place that we're comfortable actually defining the boundary conditions.